In this class, we are looking at electric field 2. We are given two similar but opposite point charges, minus Q and plus Q, each of magnitude 5.0 times 10 raised to power minus 8 coulomb, are separated by a distance of 8 cm in vacuum, as shown in the diagram below. We are to calculate the magnitude and the direction of the resultant electric field intensity, E, at the point P. We are to calculate the magnitude and the direction of the resultant electric field intensity, E, at the point P. We are to draw the lines of force due to the system of charges, and we are given our K to be 9 times 10 raised to power 9 Newton meter square per coulomb square. Our K, which is also equal to our 1 divided by 4 pi epsilon naught, is equals to 9 times 10 raised to power 9 Newton meter square per coulomb square. Okay, so this is the diagram that we are given. This is the diagram that we are given. Okay, so in this diagram, the first thing we are going to do is we are going to calculate in this diagram. The first thing we will do is to calculate our electric field intensity at point P due to minus Q charge. We want to calculate the electric field intensity at point P due to the minus Q charge. And don't forget, the formula for electric field intensity is force per unit charge. Force per unit charge. If I put that force divided by Q, that will give me minus KQ, all divided by R square. Minus KQ, all divided by R square. Okay, and our K is already given to us as 9 times 10 raised to power 9. From here, our K is already given to us as 9 times 10 raised to power 9, and the Q, which is the magnitude of the negative charge, is 5 times 10 raised to power minus 8. 5 times 10 raised to power minus 8. Okay, either you use capital letter Q or you use small letter q. The basic thing is for you to know what you have used it to represent. So in this case, our capital letter Q is also the small letter q that I have in the diagram. Okay, then our R will be the distance between the minus Q charge and point P. Our R will be the distance between the minus Q charge and point P, and that is 5 centimeter. If I convert 5 centimeter to meter, that will give me 5 divided by 100, and that is 0.05, then squared. If I press my calculator correctly, that will give us 1.8 times 10 raised to power 5 Newton per coulomb. 1.8 times 10 raised to power 5 Newton per coulomb. This tells me that if I put a charge at point P, if I put a positive test charge at point P, the direction in which the positive test charge will move is towards the negative charge. The positive test charge that I place at point P will move towards the negative charge, and of course that shows an attraction. If I put a positive test charge at P, the minus Q charge will attract it. Okay, so the direction of motion or the direction of the force will be towards the negative charge. Okay, so the direction of the force of attraction, which is towards the negative charge, will also be the direction of the electric field intensity. The direction of the force of attraction will also be the direction of the electric field intensity if a positive test charge is placed at P. Good. Now, we'll also calculate the electric field intensity at point P due to the positive charge placed here. The electric field intensity at point P due to the positive charge placed here. Now that is represented with E subscript plus, E subscript plus, which is equals to plus KQ all divided by R squared. The plus represents the positive charge. The minus here represents the negative charge that we are using. Okay, good. Now plus KQ all divided by R squared. If I put in the value of my Q, which is 5 times 10 raised to power minus 8, and the value of my K, which is 9 times 10 raised to power 9, all divided by the distance between the plus Q charge and P, and of course that is what, 3 centimeter. I will convert this 3 centimeter to meter by, I'll divide by 100, and that will give me 0.03 then square. If I press my calculator correctly, that will give me 5 times 10 raised to power 5 Newton per coulomb. 5 times 10 raised to power 5 Newton per coulomb. Okay, now since we are to get the resultant electric field intensity at P, we want to get the resultant electric field intensity at P. Okay, just like I explained earlier, if I place a positive test charge at P, this will be the direction in which the positive test charge will move as a result of the negative charge. The negative charge will attract it to itself. If I place a positive test charge at P, as a result of the positive charge, it will repel it. So the direction for the in which the test charge will move as a result of the positive charge here is in this direction. It will repel it. The positive charge will repel the positive test charge I place at P, whereas the negative charge will attract the positive test charge I place at P. And that is why my E subscript minus, E minus, is in this direction, and my E subscript plus, that is E plus, is also in this direction. Okay, good. So I have both my E minus and my E plus moving in towards the left. Okay, that is towards the minus Q charge. All right, so the resultant electric field E is represented with E and is equal to E minus plus E plus. Since both of them are acting along the horizontal, and they are in the same direction. That is why I can add them the way I add normally. They are both along the horizontal, that I can add them normally, and they are also in the same direction towards the minus Q charge. Okay, good. And that gives me my E minus is 1.8 times 10 raised to power 5 Newton per coulomb. This is it. And my E plus is 5 times 10 raised to power 5 Newton per coulomb, and this is it. Okay, so when I add, I will have 6.8. I will just add 1.8 plus 5.8, and that will give me 6.8. Then I will take one of the powers. Okay, so that is times 10 raised to power minus 5 Newton per coulomb. Okay, so the field is directed towards the left or towards the minus Q charge, just as we have explained. Thank you for your listening attention. Hope to see you in the next class. Bye.